Hi everyone. Now we will start discussing the frequency response of a common drain amplifier. Just to quickly refresh your memory, a common drain amplifier doesn't give much of a voltage gain, but it has all the properties of a good voltage amplifier. Its input impedance is very high, it should be infinity. Output impedance should be very low, which typically is in the order of 1 by gm for a MOS amplifier, and BJT also it's close to 1 by gm. So low output impedance, high input impedance, an ideal candidate for voltage amplification. Of course, the voltage gain is very close to 1, but still it's often used as a voltage buffer, but not as an amplifier, but as a voltage buffer. So now we will look at the important properties of a common drain amplifier and how do they change as a function of frequency because of these device parasitics. We are going to look at the gain as a function of frequency. We will look at the input impedance as a function of frequency. And then we will look at the output impedance as a function of frequency. And we will see how does these values deviate from their nominal values. And of course, how does it deviate from its nominal performance as well. Now, to quickly look at all the sources of parasitic capacitors, you have a drain to bulk capacitance, a source to bulk capacitance, gate to drain capacitance, and gate to source capacitance. Drain to bulk doesn't matter because both the nodes are at AC ground, so I'm ignoring it. And gate to drain capacitance will appear as an input capacitance. And I've added the source to bulk capacitance together with the load capacitance. Now first I'll analyze the circuit with Rs equal to 0. Of course, once we analyze the circuit including Rs, the analysis becomes a little bit more complicated, but we will draw intuitions out of this circuit by making some simple assumptions. So first I'll assume Rs is 0 and analyze the circuit. So when I assume Rs is 0, I'm going to directly drive this node with Vi. So CGD doesn't matter here because it doesn't require any time to charge CGD because it's directly connected to the input. There is no time constant associated with this capacitance. There is no resistive path to charge it. So I'll ignore CGD and analyze this circuit. Now, if you recall, I had analyzed this circuit when we were solving poles and zeros intuitively for MOS circuits. So we have to employ this standard procedure of short circuit transconductance multiplied by the output impedance. The short circuit transconductance can be found this way. So you have Vi, I have short circuited the output and measured the current flowing at the output terminal. So since Vi appears entirely across VGS, so the total current flowing through the MOSFET will be GM VGS, which is GM Vi, and the current through the capacitor will be SCGS into Vi. So using that, I get the short circuit current as GM into 1 plus SCGS by GM into Vi. So we saw that there is a left of plane pole here, left of plane 0 here, value GM upon CGS. And we said we will encounter 0 whenever you have two different paths, parallel paths adding together, and both the paths should have different frequency dependence. Then we will end up getting a 0. The next step is to find the output impedance. So you will have RL parallel CL in parallel with 1 by GM parallel SCGS. So we can expand that. At DC it will be just RL parallel 1 by GM. So that's what this term is. RL by 1 plus GM RL is just RL parallel 1 by GM. Then the other term, you will have two capacitors in parallel. CL and CGS will appear in parallel, and the pole will be at 1 by S CL plus CGS into RL parallel 1 by GM. So if you look at the output node, you have four impedance elements. So you have RL, 1 by GM, and two capacitors CL and CGS. So I can add these two capacitors together and the two resistors together. So this becomes RL parallel 1 by GM, and this is CL plus CGS. So what we get here is this expression. So the output impedance is simply RL by 1 plus GM RL into 1 by 1 plus S CL plus CGS into RL parallel 1 by GM. So now we multiply the two terms. We see here there is one pole and one zero, one left of plane pole and one left of plane zero. here. So this is the left offline pole and 0. And what we will do is very quickly analyze the circuit intuitively and see how does this common drain amplifier behave under limiting or the boundary conditions. So that is, first at DC, how does the circuit behave, and at infinite frequencies, how does the circuit behave, and then we will try to correlate it with this response. So at DC here, I have open circuited all the capacitors. So it's a simple common drain amplifier, and we get this expression GMRL by 1 plus GMRL, and I have derived this a lot of times. So we have derived it in multiple ways. So you get an expression GMRL by 1 plus GMRL. At very high frequencies, at infinite frequencies, RL will be shunted out by a capacitance CL. So we'll have CL here and CJ here. Now the output voltage across CL is simply the current flowing through CL, which is nothing but the sum of the current through CGS plus the current through GM, the device. Now let VGS be the gate to source voltage across the MOSFET. Then the current through CGS is given by S CGS into VS, and the current through GM is given by GM VGS. So the total current is GM plus S CGS into VS. But one thing that we have to keep in mind here is that at very high frequencies, as frequencies I have assumed it is infinite frequency. So this term SCGS is a frequency dependent term. This is going to be much greater than GM. So I can ignore GM current altogether. I can ignore the current flowing through 1 by GM altogether. I'll have to only consider the current through the two capacitors. Now at very high frequencies, it just reduces to two capacitors in series. So you have CL and CGS. So it simply reduces to something like this. So now we are supposed to find the transfer function of this circuit. The transfer function of this circuit is a simple potential divider. You get CGS by CGS plus CL times VI. So at very high frequencies, the gain becomes CGS by CGS plus CL. If your CGS is much smaller than CL, this will be much smaller than 1. So the frequency response graph will look something like this. At low frequencies, you have GMRL by 1 plus GMRL, which again is very close to 1. At very high frequencies, it becomes CGS by CGS plus CL. So which is obviously less than 1. So if I want to go from a higher to a lower value, you should encounter a pole first and then a 0 next. The location of the 0 we saw was GM by CGS, and the location of the pole was dependent on 1 by CL into RL parallel 1 by GM. I'm going to assume GM is large. GM RL is much greater than 1, or I can say RL as a resistance is much greater than 1 by GM. So I can approximate this pole location to 1 by, the exact expression is 1 by CL plus CGS multiplied by GM. Since we assumed CL plus CGS to be greater than CGS, which is true as well, is that this pole will occur before the 0. Okay, so this is how the frequency response of a common drain amplifier looks like. Now one must wonder that, of course, the gain is going to remain constant for higher frequencies. So is it not a good amplifier because your gain is constant in this range? But you should remember, the whole purpose of a common drain amplifier is that your source is not able to drive the load directly, which means source is not able to provide that current. Ideally, you should draw 0 current from the source. But we just saw at higher frequencies, the current that is charging the capacitance CL, the current that is flowing through CL is entirely or mostly due to the current from CGS, which means most of the current is being drawn from the input source. So that's why there is no amplification. The amplifier is no longer behaving as an amplifier. For an ideal amplifier, you should have power amplification. The power delivered to the capacitance or the output load should be greater than the power drawn from the input. And that is violated at very high frequencies, so it no longer behaves as an amplifier. So we discussed, even though common drain amplifier's gain is just 1, it offers a huge power gain because of the current. All the current is given by the amplifier itself to the load. But now you see, all that current is entirely coming from the input, so it no longer behaves here. It's not an amplifier in this region. In this region, it's behaving as an amplifier. Now, we will look at what happens to the circuit when you have a finite source resistance. The whole idea of going for a common drain amplifier was that when we began discussing common drain amplifiers, we discussed that if you have a source resistance, a voltage source directly driving a load resistance, most of the voltage will drop across RS itself. That was the reason why we introduced a common drain amplifier. We wanted this common drain amplifier to serve as some kind of an impedance transformer. We added a common drain amplifier so that it delivers the same voltage to the load as Vs. It doesn't give any amplification, but the impedance seen at the output is independent of Rs. It should be independent of Rs. It should be much smaller, and we saw it for a common drain amplifier is 1 by Gm. Similarly, as far as the source is concerned, the input impedance should look like an infinite impedance. It should be infinity and independent of RL. It should have no dependence on RL. That's the condition we'll have to meet. That's what a common drain amplifier is designed for, as an impedance transformer. For source, it should look like an infinite impedance. For load, it should look like a very low impedance. Now we'll see what happens when you add a source resistance. Now again, the mathematical analysis becomes a bit more complicated. So I'll just tell you roughly how to do the analysis and how to, I'm mainly going to show you that the zero location remains the same and roughly how the function will look like. So to do that, we'll start with our standard procedure. We'll find the short circuit transconductance and then multiply it with output impedance. To find the short circuit transconductance, I've grounded the output node and I'm going to measure the short circuit current flowing at the output node. So since output is at ground, I'll also include CGD in the analysis. So I'm including CGD here. So what you will get here is that at the input the circuit is, you have RS and CGD plus CS. It looks very similar to common source amplifier's input. Okay. You are measuring the short circuit current. So it will look very similar to that of a common source amplifier. And the transfer function here from input from Vx to Vi or Vi to Vx is 1 by 1 plus SRS into CGD plus CGS. That's the voltage at this point. Now once you know this node voltage Vx, the output current is simply given by the current through the capacitor plus the current through the MOSFET. That is simply Gm plus SCGS into Vx. So Gm Vx plus SCGS into Vx, you get this. So now the overall the short circuit transconductance or the short circuit current is given by Gm into 1 plus SCS. Again here I have taken Gm common out. So I'm going a little fast here because this is something we have already done. Gm into 1 plus SCGS by Gm into 1 plus SRS into CGS plus CGD. So if you see here, even in this case, the 0 remains the same. The 0 is at 1 plus SCGS by Gm. Okay, the 0 here it is at Gm by CGS. It's a left of plane 0. Now to find the output impedance, again this output impedance will be a little bit more complicated. So what I'm going to say roughly is that one thing that you can show in this output impedance is that the output impedance will have a 0 at CGS RS. It will have a 0 at this term. So that 0 will cancel out this pole here, but you will have 2 more poles in the system. So it will eventually have 2 poles and 1 0. The system is going to have 2 poles and 1 0. Okay, but what we will do is that we will look at, I have already analyzed how does the circuit behave at very high frequencies. If you see now, the circuit at very high frequencies, at infinite frequencies, it's going to behave like this. So you'll have 2 capacitors, CL, CGS and RS and Vs. So previously, if you recall, we said that the current was entirely coming from Vi, so there was a direct potential division at the output. The potential division voltage at the output was CGS by CGS plus CL times input. But now there is also RS. So then how do we calculate the output voltage? I'll again use the approximation that the current through the capacitors is what that matters in the end. That's what dictates the overall response. So I can see that that current through this capacitor CL is entirely coming through CGS, and again that current will also entirely come through RS. So now the circuit reduces to something like this. You have PS, RS, CGS and CL. The circuit reduces to something like this. Now I can find the voltage at this point. We know how to find the transfer function here. You can assume these two capacitors are in series. So the circuit reduces to a simple resistor RS and a capacitance of value CGS-CL by CGS plus CL. So the transfer function to this point will be 1 by 1 plus S RS into, I'm going to call this term CGS-CL by 1 plus by CGS plus CL as CGS parallel CL multiplied by, so you know the voltage at this point. So the voltage at this point V0 will simply be CGS by CGS plus CL. So now you can see that at high frequencies the gain is going to decrease because you have a pole now at high frequencies, so the gain is going to decrease significantly. Okay, so that's what we can see from this expression here. The important thing to understand here is that, as I said even before, the current at very high frequencies is entirely coming from the source itself, and that should not happen. An ideal voltage buffer should draw no power or current from the input. All the current that is delivering to the load should entirely come from the amplifier itself. That's what we would ideally want, but at very high frequencies the buffer is completely bypassed. So it looks as though the buffer is not providing any current. The entire current is entirely coming from the source itself. Now we will look at the two other important parameters of a common drain amplifier, which is its input impedance and output impedance. Now we said these two are very important parameters when we look at common drain amplifiers, because the whole idea of designing a common drain amplifier is so that it can serve as a buffer which can offer very high input impedance and very low output impedance. The important condition is the input impedance should be independent of load resistance. Whatever be the load, input impedance should be very high and it should be independent of RL. Now I have drawn the circuit here. For simplicity, to show you what's happening in the circuit, I have ignored CL, I have ignored the load capacitance, and I am only trying to find the input impedance in this case. Intuitively we can analyze this and try to find it, and of course we'll also do a rigorous analysis as well, but we'll first find it intuitively. Intuitively, at DC or omega equal to 0, the capacitor is open circuit, so the input impedance will be infinity. At very high frequencies, the capacitance acts like a short circuit. If the capacitance acts like a short circuit, the VGS is 0. The VGS is 0, there is no current flowing from the MOSFET. So all the current, when you apply a test voltage Vx here and measure this current, it's going to flow through RL. So RL, because it is a short circuit here, will appear directly at this gate node. So the impedance there will just be RL itself. So at infinite frequencies, the input impedance will just be RL itself. So this is how the input impedance at low frequencies it will be infinity, at very high frequencies it will be RL itself. What is the exact expression? I will derive it in a few moments using some interesting approximations. The next part is to analyze how to find the output impedance of a common drain amplifier. To find the output impedance, again I have neglected the load resistance and capacitance, and I have also ignored CGD because I wanted to show how it depends on RS. Again we will find the limiting values or the boundary values at DC. At omega equal to DC is 0, this capacitance is an open circuit, so the looking in impedance is just 1 by Gm itself. At very high frequencies, at infinite frequencies, the capacitance will act like a short circuit and the output terminal will directly see the source impedance. So this RS will appear directly at the output terminal. So it looks like the amplifier is getting bypassed. The whole goal of putting this amplifier in between the load and source is that this amplifier is going to transform this impedance and going to offer me an impedance of 1 by Gm which is independent of RS. That's what we wanted this amplifier to do. But now what we are seeing at infinite frequencies, because of these parasitic capacitors, is that it's losing its ability as an impedance transformer. It's offering a very high output impedance, which is equal to the source impedance itself. In the same way, at the input also, it's supposed to offer a very high input impedance, but it's becoming equal to the load resistance itself, which is not desired. So that's the problem that parasitic capacitors cause in case of a common drain amplifier. In the next lecture, I'll tell how to derive an exact expression for the input impedance of a common drain amplifier using some interesting approximations. Thank you.